All right, next up here, we're going to write these tables in as exponential equations in this form y equals a times b to the x. This is it should look a little familiar to you. We used to, in sequences, geometric sequences, we used to do these as a sub n equals a sub 0 times r to the power of n. And so that's really the same idea here. And so I'm just going to define these here in this equation up here as a is equal to f of 0. So whatever the y value is when x is 0, that's our a value. And then b is really the growth rate. And so that's kind of what's being multiplied every time we increase by one x value. So what I can see here is that on number 11, for example, f of 0 is obviously 1 right there. So that means that a is 1. And then what's happening every time is it's being multiplied by 2. And so that means that the growth rate, or b, or r as we used to call it, is 2. And so my equation for number 11 would be, actually I was going to write a sub n, but let's do it as y equals 1 times 2 to the power of x. And obviously for that one, if you could also write it as y equals 2 to the power of x, because that 1 is insignificant since it's a multiplier. All right, so then number 12, you can see that they gave you f of 0 again. So that one is a will be 2. Actually, let me do this in a different color. All right, now the growth rate here is a little trickier to see, and the reason why is here we jump 2. And so what I kind of need to figure out here is what would be like the intermediary step here along the way. And so what would I have to multiply by here? Well, I'd have to multiply by 9. So that really means I'm multiplying by 3 twice. And so I can kind of visualize here that if this table was continued, there would be 1, 9. Oh, no, sorry, it wouldn't be 9. It would be 6. And then it would be 2, 18. And then I can really see that times 3 pattern. And then I'll just double check that here. Does this make a times 3 pattern? And I see that it does. And so that tells me that my b is 3. And so I'm going to say here that y equals 2 times 3 to the power of x. You can always check this. You can plug in any point and it should kind of correctly predict this. And so if I kind of do this on my calculator as y, or actually I'll do it as f of 4. So f of 4 equals 2 times 3 to the 4th. And if I type that in my calculator, I do get 162. So that one checks out. So that's just a way you can always check it. All right, next up here we got number 13. So once again, we do have our a value here at negative 1/3. And it is possible for a to be negative, that's fine. All right, and so now we got to figure out what's our growth rate. And so what I am tracking here is that this is being multiplied by a positive 1/3 as it goes along. I see that again there. So even though all the numbers are negative, they're not changing, and so for that reason I would say that this is 1/3 and then this is negative 1/3 out front to the power of x. Remember that we cannot multiply those two together because of the exponent on the second one, so we're just going to leave our answer like that. All right, and then lastly here, number 14. Oh, and one more thing, this is decay because the numbers are getting smaller along. Oh, actually, they're getting to be smaller negatives, which are actually bigger numbers. Never mind. The next one, number 14, is definitely decay, so let's talk about that one instead. Yeah, usually on a problem like 13, they don't really classify those as growth or decay. And so on number 14, I would actually look for this one right here, since the x's are increasing by 1. That tells me kind of what's the growth rate here. And it's actually a decay rate, so it's going to be times 1/2 as we move along. So that's going to be our b value. And then we know that our a value there is 4, as that's our f of 0. And so I would say that's y equals 4 times 1/2 to the power of x. All right, next up here, number 15, we're going to kind of do a similar thing here with this one. So we see once again that we know that this is going to be our a value since that's f of 0. And then the growth rate here is what's being multiplied as we go along. Now you can see that this skips one, so there's another way we can do this. I'm just going to go ahead and plug in 3 as my a value. And I'm going to leave everything else. And then we're going to plug in this other point as our x and our y. So if I say 75 equals 3 times b to the power of 2, and then we divide each side by 3, we say 25 equals b squared. And then we would square root both sides. I would say b equals plus or minus 5, but technically the base on these always has to be positive. And the reason the base should always be greater than 0. If it's less than 0, then you have a negative number, and if you have like fractional exponents with that negative number, they're not going to be graphable. So on all these, I would always kind of assume that b is positive. So then I'm going to say b is 5, and we'll say y equals 3 times 5 to the power of x. Okay, same idea here. So we know that a is going to be 48, and then I'm going to plug that in. So we'll say y equals 48 times b to the power of x. And then I'm going to plug in the other point as my x and my y. So I'm going to say 3 equals 48 times b to the power of 4. I'll divide by 48, which I'm pretty sure that reduces. Yeah, that's 1 over 16 equals b to the 4th. And so now I'm going to do the 4th root. Now, if you don't know where your 4th root button is, I actually, instead of that, like to raise this to the 1/4 power. That is the same thing as the 4th root, but sometimes it's a little easier to type that in. Do make sure, though, you put that in parentheses as you're typing that in the calculator. So 1/16 to the power of 1/4. And that's going to give me 0.5, which I know that means b is 1/2. And so I'll say y equals 48 times 1/2 to the power of x. All right, next up here, number 17. I actually see right away we have a little typo here. So if you guys could just fix this to say years after 2012, that's kind of what I meant for that to be right there. Okay, so it says Mr. Barry bought his car in 2012 for $12,500, and so that's going to be our a sub 0. That's going to be our a. And then it says in 2017 it's going to be worth $40.96. So I'm going to see that as a point. And since we're starting at 2012, I'm going to say that this is 5 years after 2012, and that's going to be $40.96. And so I know right away that I can write this as v equals 12,500 times b to the power of t. And then I can plug in my other point from up here. So that's going to be 40.96 equals 12,500 times b to the power of t. I'm going to go ahead and divide that 12,500 over. I'm just going to leave that as a fraction. Oh, and you know what? I should have plugged in this as 5 for t. Shoot. Okay, and so that'll cancel out. And so then I have b to the 5th power equals 4096 divided by 12,500. I'm going to raise both sides to the 1/5 power, which is really taking the 5th root here. And so I'm going to say b equals, make sure you put the 1/5 in parentheses, and also the other fraction in parentheses as well. Always with fractions, with exponents, you always want to use parentheses in these cases. Okay, and so I get that b is 0.8. A nice kind of only one decimal number there. All right, so I know that v equals 12,500 times 0.8 to the power of t. All right, and so I'm going to use that equation to kind of, what do you call it, continue on with this problem. So by what percent does the car decrease in value each year? So that's going to be based on the 0.8 right there. But when we're talking about increase or decrease, and we talked about this a lot when we did geometric sequences, it's always as compared to 1. And so this one, how much less is that than 1? It's 0.2 less than 1. So I'm going to say 20% here, because 0.8 is 20% less than 1. And so always, whenever we're talking increase or decrease of a percentage, always compare that to 1. All right, next up here, I'm going to answer the last question. So how much will be worth in 2022? And so that's t equals, let's see, we're starting at 2012. It's just going to be t equals 10. And so 12,500 times 0.8 to the power of 10. And so that's going to be 1342.18 if you round that to the nearest penny. And this is pretty typical of cars. Cars kind of always decrease in value as you use them. All right, next up here, we got a very similar problem. And so we know we're starting at 2011. So this is going to be our A sub 0, or our, just call it A. And so I know that it's going to be V equals $320,000 times some B value to the power of T. And then so our other point we have here is that after 4 years, it's worth 388,962. So I'll go ahead and plug that in. All right, so then we'll divide that over. So I'm going to go ahead and write it over here as 388,962 divided by 320,000 equals b to the 4th power. So now we will raise both of those to the 1/4 power, or do the 4th root, same thing. And I'll go ahead and do that in the calculator to find out what b is. So we got 388,962 divided by 320,000, and then to the power of parentheses 1/4, and that's going to give me 1.05. And so I would say V equals 320,000 times 1.05 to the power of T. All right, so then by what percent does it increase each year? And so once again, we're going to look at that growth rate, 1.05. And since the wording is increase, we compare it to 1. And so I'm going to say that's a 5% increase, since 0.05, actually 1.05 is 5% more than 1. So if it was exactly 1, that would just be staying the same. So this is 5% more than that. So it's going to be a 5% increase. This is kind of typical more for real estate, like condos and houses. They usually increase in value over time. All right, so then how much will it be worth in 2040? So how many years is that? So that'll be 29 years after 2011. Right, yep. And so I'm just going to say 320,000 times 1.05 to the power of 29. And that's going to be worth, we got $1,317,163.39. Some of you may think that that's crazy, that a condo, which is kind of like an apartment would be worth over $1 million. But I don't know, my house, if you looked at like how much my house was worth in 1970, it was worth like $20,000, and now it's worth like $750,000. So real estate prices do kind of always go up, especially in Orange County. Everyone wants to live here, so this is kind of not that surprising to me. All right, that's it for today. I'll see you guys later. Bye.